Hello? Hello?
Okay, so good morning, everyone. Today we are going to talk about hyperparameter tuning, and we will use KNN as an example for you to understand how to do hyperparameter tuning in an automatic way. Okay, and please first download the notebook from OLE and also the dataset, the iris dataset in OLE. Okay. What to put the dataset? After you've downloaded the dataset, please upload the dataset to your workspace, the files, okay? Okay, then let's start. Okay, so the first cell is about some libraries. Just run it. And today we are going to use a new visualization tool. Okay, it's very similar with matplotlib, but it's from Seaborn or CSNS. Okay, just another visualization tool. And then at the beginning, we need to first read the dataset. Okay. So I think you've already very familiar with this operation, pd.read CSV. And then put your iris dataset. So this iris dataset is about flowers, 鸢尾花. Okay. So I will show you later. Okay, and then in the head. Okay, yeah, you can have an overview of the dataset. So this is about 鸢尾花, and we have different species, 不同种类的鸢尾花, different species of iris. Okay, that species here. And we have in total 3 different species. And what we are doing is that we are going to recognize what the flower, what the iris belongs to, what species according to the features here. So this is like sepal length, sepal width, petal length, petal width, 花瓣长度、花瓣宽度、花萼长度和花萼宽度。Okay, so we use these 4 different features to decide what kind of species it is. Okay, then when we are tackling these kind of data sets, we can first have a look at its shape. Okay, usually it's very important because it's like the input of your model. So we can see we have in total 150 rows, means 150 samples, and we have 6 columns. So yeah, 6 columns here and 4 features here. The first column is just the ID, the item, the ID of the item. Okay, and then we can also have a statistical summary. I think we've used this before, right? Describe. several classes before we use it, I think. So it's like it shows you the statistical summary of different columns. Okay, it's like how many samples and what's the mean value, the standard deviation, the mean value. Sorry, this is a mean. It's like a minimum. Okay, minimum value, and this is lower 25%, 50%, 75%, and the maximum value. Okay, and also yeah, just like for revision, we've used this is now function, right? To check if there are any missing value in the data set. Because it's a very official data set, it's a very famous data set. And so the data is well pre-processed. We don't have any missing data here, okay? But it's just the routine when you get a new data set. Okay, and get the distribution of target variable, okay. It's like we want to have a more, let's see, have an overview of the species, the number of species. I mean, the number of iris in each different target value or in each different species. So we should count plot. We can use the count plot function in this SNS plotting library. This is like a histogram. So we use the species column, species column. The data is here. Here. Okay. Yeah. Yeah. And then we can see that we have a balanced data set. So all samples from different species or different categories are the same. So this is a balanced data set. Okay. So if it is a balanced data set, it is good to use accuracy as a performance matrix, right? That we talked about in the lecture several weeks ago. Okay. So this is like the overview of the data set. When you have a new data set, you need to check these things before you use it. And then we can do feature selection. So yeah, so sometimes we want a less complex model with less features to make the model more efficient and save the computation time, right? And so we can do feature selection before we train the model to find out the most important features. And so firstly, let's get all the features from the data set. So we use this, we create a new data frame, okay, based on the columns that we define here. So the X column, for the training data, X, we have 4 columns here. And for the Y data, the target value, we only have 1 column. And the important thing here is that please pay attention to these extra brackets, okay? So this is like when we are extracting columns from a data frame, we need to, if we have multiple columns to extract, we need to create a list. Okay, so this one is a list of the columns that we want. And then we put in the df function, okay? And then we got the columns that we want. So please don't forget these 2 extra brackets to create this list of the labels of the column, labels of the column, not labels of the data. Okay, after we run it, again, we do train test split. We've done it for many times, right? Train test split. And we have X, Y, test size. So test size we use the 0.25, 25%. We put a random state, create a random seed, random state. 20 state. Okay. And then we see what we have. So we've split the data set into a training data set and a test data set, right? And so in the training data set, the dimension or the shape of the data is 112 by 4. Okay, so it means we have in total 112 samples inside this data. And for each sample, we have 4 features. And this is target value. We have 112 corresponding target value. And the shape is 1, okay? So it is omitted. And these are the same. We have 38 samples in the test data set. Yeah, so this random state is just like a random seed, okay? It makes sure that every time you split the data set, they split in the same way, although it is a random way, but in the same random way. So the data set, the training data set and test data set will be the same every time you run this code if you define the random state. Okay, you can put any value, I think, here. Here we put 0, it doesn't matter. Okay. So then we can do feature selection, okay? And then you just need to have an idea about these things. And you don't need to fully understand, but I mean, if about this algorithm to do feature selection, okay? But if you are interested in this, you can have a look on some YouTube videos about the criterion on how to define the importance of the features. So let me first put the code here, and then let me explain a bit. Okay. So here we use a test called chi-square test. Okay. So the name of the test is like a chi-square test. 卡方检验. This is used to test the dependency of different variables. And in this case, we use this test to check if the features in each column is related to the target value and how much they are dependent, how much they relate to each other, okay? So if the relationship between the feature and the target has a very high score, so it means they have a very high correlation. And then if they have very high correlation between the feature and the target, it means this feature is more important in make decision on what the flower is. Okay. And then here we can see that we have scores here. The higher scores in this chi-square test means higher dependency between these two variables. 这边我们做了一个卡方检验，然后卡方检验的作用呢，就是检测 x 和 y 之间联系大不大。 如果 x 和 y 之间联系比较大的话，那就说明这个 x 对 y 的影响比较大。如果 x 对 y 的影响比较大的话，那就说明这个 x 比较重要，对吧？然后如何判断这个 x 重要不重要呢？我们就根据它的 score 卡方检验的分数，分数越高就说明这个 x 越重要。Okay, so this is like how we do feature selection. And then print out, we have 4 different scores for different columns of the features. And this is their corresponding label of the column. Okay. And then also we have another way, but it's called ANOVA. FGN. Okay, ANOVA test. This is, let me see, FGN. F classify. This is, we use F test. The principle is the same as what we've done here, okay? So we just bring the scores. This is like different method to decide the score. And then we also have some scores here. We can still say that although we've used different criterion or different test method to test the dependency between variable and the target, between different variables, the results are similar, that the third column and the fourth column, the third feature and the fourth feature are much more important than the first 2 features, as they have much higher scores than the first 2 columns, okay? Which are petal lengths, petal weights. So here later we are going to use petal lengths and petal weights for prediction. Okay. Then we can do some pre-processing. So firstly, we define the fit, FT here, right? Feature selection here. And then according to this feature selection, we do a transform on the data. So we choose, because we've defined here the top 2 features, okay? And then it will automatic select the top 2 features in these 4 columns. Oh, sorry, in these 4 columns, okay? So we just use transform here, ft.transform. To use this ft, we decide here, okay? And then it will automatically select the 2 columns that we want. And we use these 2 columns as a new training data set and a new test data set. Okay, and then we done this for many times, use the scalar to do normalization. Actually, here we are doing standardization, and I've mentioned this in the lecture this week, standardization. Okay, so it's like the standardization is like let's see, the formula is like this. X. Okay, for each data point, the data point is deduced by its mean value and then divided by the standard deviation. Yeah, and after you apply this formula, so this mean value means the mean value of the feature, okay, and the standard deviation also means the standard deviation of the feature of each column, okay? So when you are doing standardization or normalization, you are always doing on each column. So after you've performed this operation, your data, your features will have a distribution of mean value of 0 and standard deviation of 1. Okay, so this is called standardization. Okay, so you can replace normalization by standardization. So you can choose either of them, doesn't matter. Just like to rescale the data. Okay. And then let's see what we do. Oh, so here we use the the PNN, right? So we just need to use the same thing as we used in the previous labs. Okay, key neighbor classifier. Okay, and then neighbor and number of neighbor equal to I. Okay, so because the I, we are going to check the value for each different key value from 1 to 20, right? This we've done before. Okay, we've already done in the, I think 2 weeks ago, right? And feed the data. Next screen. And Y string. Okay. Here we use the predicted value as the result. Yeah, and predict. We use the classifier to predict according to the X, the test set, the test data. Okay. Yeah, so this is the accuracy. And then we can print it out. Yeah. So this is accuracy when we are using different key values in the KNN. Okay. So this is like this. So it's like when we set the key value as 4, we reach the optimal result, optimal accuracy. Okay. And then we can do parameter tuning in an automatic way, actually. So let's see. So here I need to introduce this grid search. Okay, so this is a automatic method to search the optimal parameter, optimal hyperparameter for the model. Okay, so let's first import the method, the library. And then here is how we define the candidates. Okay, so let's see, we want to check what is the best value in the number of neighbors, like the key value, with the combination of different distance metrics. So this I've also mentioned a bit in the lecture, that we have different metrics to measure the distance. And previously we were using the Euclidean distance. And also we have Minkowski distance and Manhattan distance, okay? So if there are 3 criterion to measure the distance, and if you are interested in this, you can have a look in the YouTube or in Google, okay? I'm not going to explain the detail about how to calculate different distance, because it will take too long time. Okay, but the point here is that we want to know, because we have 2 different hyperparameters here, and we want to see what's the best combination between different hyperparameters. Okay, but because here we've defined that 4 is the best value for key, right? However, this is based on the default distance we set here, that is the Euclidean distance. And then when we are using different distance here, the result might be different. So it means when you're using a Manhattan distance, maybe the optimal key value is not 4, it will be 5 or 7, something like this. Okay, that's why we need to check what's the best combination of parameters. Okay, and then we just need to define a grid search. Okay, we use the grid search CV, grid search cross validation, and we put the key neighbor classifier. paste right here. We define in this grid search CV, you can first define your method, your model. Okay, here we use KNN model, and then we define the parameter that we want to search. Grid parameter. Okay, so I just copy paste from here. Grid parameters. And here are some other parameters. Variables. Okay. And variables define the details of the of the search. Okay. CV. This is called cross validation. And we talked about in the class, right? Cross validation. So here we use threefold cross validation. It means we separate the data set to 3 different subsets, and we do 3 times training. And in each time of training, we test on one of the splitted data set. Okay. So this is called cross validation. And this we can also define the N jobs. N jobs means if we can enable the parallel processing. So if we put this as -1, then it will use all the available CPUs of your computer, okay, to do the processing parallelly, because you need to repeat this process for many times. Let's see here. Yeah, we've talked about it. So we've defined 2 different parameters. Hyperparameters. And in the first hyperparameter, we give 6 candidates. And in the second hyperparameter, we give 3 candidates. And for each time, we run the model for 3 times for cross-validation. So in total, we need to run 54 times with different hyperparameters in different combinations. So it will take some time. That's why we need to run it in a parallel way. Okay, we need to use different CPUs. If we have different core CPUs, we can run them parallelly. Okay. And then very easy. Just feed the model again. Okay, here we use the GS. We define the GS here. gs.feed. And then the training data. Let me find the training data here. Okay. It's the same what we've done here. So the training data inside to feed the variables of X and Y. Okay. Yeah. So we've run 3 folds for 18 candidates. So in total, 54 bits. And then we can print the best score. So in this 54 times of training, the best score we got is the accuracy of 0.9956. Okay, so it means 95.56 accuracy. And then the best parameter for this best accuracy is this, based on Minkowski distance and the number of neighbors of phi. Okay. Yeah. Okay. And then, so by default, we are using accuracy. So here, what means best score? So when you are using this, I think there's another parameter called scoring. Yeah, you can see here, scoring. So by default, the scoring is the accuracy, okay, for classification. And also you can define the scoring by yourself to the recall rate or precision or F1 score. Okay, but by default, it is the accuracy. Okay, then use the best hyperparameter. Yeah, okay, so we'll use this best hyperparameter. Just train a new model based on the best hyperparameter, which number of neighbor is 5, and the distance metric is the Minkowski distance. Right, and fit the x data and y data. Okay. Oh, sorry. That I have a spelling mistake. Yeah, sorry. Okay. So we have a new trained KNN classifier, and then we do classification on it. Okay. Yeah. So we already have code here. We just run it, and then we have a classification result. So y hat is based on the training data, the classification result of the training data, and YKN is the test result. Okay. And then we start to do model evaluation. Just all the code are already available here. Okay, so we just run this because we've already done model evaluation for many times. So yeah, so in the end, we got like test set accuracy of 97.36. Okay, and the training accuracy here. Okay, we have different accuracy in training set and test set. This is also like the confusion matrix we've done before. Tell you how each class confuse each other. Let's say in the test set, we have in total, how many? 38 samples, right? And then one of the sample is misclassified. Okay, so only one sample is misclassified. Okay, and then here is a classification report. Yeah, more comprehensive classification report of different performance metrics for different classes and the average accuracy. Okay, this classification report. That we've also talked about this in the very beginning, I think 2 or 3 weeks ago, right? Okay, and then when we are doing cross-validation, we have an easier way. We just want to do cross-validation. So we put the whole data set, X and Y, this original one, okay? At the beginning, we defined at the beginning. X and Y here. Define X, Y here in the beginning. Okay, this means the whole data set. And then we directly do cross-validation without train test split. Okay, we add the data. Okay, here we do it without train test split. We do a cross-validation of 5-fold. So we split the data into 5 different subsets. And then we train the data for 5 times. And each time we train the data with different subsets, all of the different subsets, and then test on the remaining one of the subset. Okay, this is a cross-validation, and it is 5-fold. You can change to 10 or other value, doesn't matter. Okay. That's it. And this is the average accuracy of your 5 tests. Yeah, okay, so this is the things today. And the part 2 is for you, for your homework. Okay. And you still have 10 minutes to have a look on the code here. And if you have any problems, please let me know. More important, right? Okay, so thank you very much. And this is the end of this lab, and see you next week.